Welcome to Saitechinfo channel, my dear students. In this tutorial, I'll be discussing about the conditions of a sustained interference. Then we'll be discussing about the bandwidth also. Okay, right. Let me take the first aspect. Condition of sustained interference. There are three important conditions. One is the two sources should be coherent. Second, the two sources should be, that is the coherent sources should be as narrow as possible. It should be very narrow. So you can consider this diagram. A, B are the coherent sources and the primary source is S. So we treat this double slit as, that is, coherent sources A and B. So these two sources should be as close as possible. That is the distance between A and B, that we already discussed as under case, that is D, small d. So the d, small d should be as low as possible. Then the sources should lie very close to each other to form distinct and broad fringes. Okay, so these are the essential thing. And let us consider, I think we have already gone through this diagram. That is, S is the monochromatic source of light and AB are the coherent sources of light, and they are kept closer to each other. And XY is the screen where the light is diffracted and from A, and another light is diffracted from B, and they interfere at we can say some point P or Q. So here Q. Okay, right. And so this is the pattern, and we are able to get this pattern alternative, that is a bright band and dark band. Okay, so the fringes will be like this. Now we are calculating the expression for the the bandwidth. So let us consider this diagram. Here D, the capital D is the distance between the screen and the coherent sources. So let me consider the center point O, and at point P on the screen interference occurs for a particular band. So let me consider this band. Central is the bright fringe, and it is enveloped by dark fringes and again enveloped by bright fringes. So likewise, alternatively, the fringes are spreading. So let us draw AM. What is AM here? That is the diffracted wavefront starting from A, and AM is the that is the wavefront. So let us consider this as a right angle. So AM is perpendicular to the BP. What is BP? So BP is the ray diffracted from the narrow slit B. Okay, so the ray diffracted from A, the ray diffracted from B, they meet each other at P, and that causes the interference. I hope now it's clear. Okay, so this AM subtends an angle theta. The AM subtends an angle theta, and being perpendicular, so AM is perpendicular to BP. Are you able to follow? Now the path difference here is, that is BP is the longer one, AP is the smaller one. So that makes the difference in the path. So BM is the path difference, is it not? So the path difference BM, which is nothing but what? BP minus MP, and both of them are equal. So you can consider AP also. So BP minus AP. So AP is equal to MP, that we already know. Therefore, delta, that is the path difference, is BP minus AP. Is it clear? So this sigma, that is BP minus AP, which can also be BP minus MP, which is BM. Is it not? So this is the path difference BM. And at right angle ABM. So BM is equal to D sin theta. So you can put what is sin theta. Let us consider ABM. Where is ABM? ABM. There is a small right angle here, and M is the right angle. So what theta here? So opposite side is BM. So what is sine theta? Opposite side by hypotenuse. Hypotenuse is nothing but AB, which is the distance between the coherent sources. Is it not? And therefore, sine theta is equal to BM by AB, which is nothing but D. So BM by D. Okay. And what is BM, which is nothing but D sine theta. So here the theta is very small, so sine theta becomes equal to theta. Therefore, we have got already here, that is sigma, which is nothing but Bm. So in place of that we can put d sine theta, where here d sine theta is almost a d. So you can put sine theta is equal to theta, and d into sine theta. Instead of that you can put d theta or theta into d. So the part difference is theta into d. How to represent the part difference here? That delta. So in right angled triangle COP, where is the COP? Let us consider COP, this right angle COP, is it not? And which is the hypotenuse? CP is hypotenuse, and theta is here. Opposite side is OP, adjacent side is OC, is it not? Now let us find out tan theta, which is nothing but that is OP by CO or OC. So OP is nothing but X, and OC is nothing but D, capital D, that is the distance between the coherent sources and the screen. So OP by OC, that is X by capital D. I hope now it is very clear, is it not? Now tan theta is equal to X by D, and tan theta being very small, theta is very small, so tan theta is equal to theta. So you can put theta is equal to X by D. Here we already know the part difference is what? Theta into d. So instead of theta you can introduce xd, x by d. So now we have delta is equal to xd divided by capital D. So the part difference can be represented as the product, the ratio between the product of x and d to d, capital D. So what is x? It is the distance of the particular interference pattern from the center. And what is d? It is the small d is the distance between the two coherent sources. And what is capital D? Capital D is nothing but the distance between the coherent sources and the screen. Is it clear? Now let us talk about the bright fringes. For bright fringes, the order, that is n is equal to order, so 0, 1, 2, 3, 4, etc. So that indicates the order of bright fringes. So we can put x is equal to, xd by d is equal to n lambda. Therefore x is equal to d by d into n lambda. So this equation gives the distance of the nth fringe from the point O. Now look at this. This can be measured experimentally. This x can be counted, measured. Then d is also an experimental value, that is nothing but the distance between the screen and the sources. Then small d, the distance between the two coherent sources. Okay, after all order is n, that we know. So based on this we can calculate the wavelength of the incident light also. So this is one of the applications here. Then dark fringes. Dark fringes are given by, that is the order here is 1, 2, 3, etc. So that indicates the order of the dark fringes. So in that case you can introduce the part difference, delta is equal to 2n minus 1 into lambda divided by 2. So that is the condition for this dark fringes. Okay. Then the equation gives the distance of the nth dark fringe. So with the help of this we can calculate the nth distance, or if we count the n we can find out the lambda also, either way. Okay. Then what is bandwidth? Bandwidth is, we have got for instance third ring and fourth ring. So the distance between the third dark ring and the fourth dark ring and the third dark ring, or fourth bright ring and third bright ring. So that makes sense, is it not? So the distance between, generally saying it can be n plus 1th order and n, or and nth order, or between the two consecutive bright fringes, okay, from O. Therefore, xn plus 1 minus xn is equal to d by d into n plus 1. So, as far as bright fringes is concerned, you have to use n plus 1 into lambda. For darker one, you have to use 2n minus 1 into lambda by 2. Okay, so that is the equation we have to maintain. So, d by d into n plus 1 whole divided into delta, I mean lambda, minus d by d n lambda. So, this is n plus 1, this is n. So, we have to subtract, and finally we get d by d into lambda, where from we have completely eliminated the order also. So, in that case, what is bandwidth? The bandwidth, the beta, is given by d, capital D, divided by small d into lambda. So, it gives a certain features saying that beta, keeping lambda constant, beta is inversely proportional to d. So, narrower the d, small d, that is the distance between the coherent sources, and the bandwidth will be clearer, brighter and clearer, that is wider. And what about the distance? The distance, when the distance between the screen and coherent sources increases and there is a chance of more interference, so we are able to get better bandwidth. Okay, so that is directly proportional to capital D. So these things are very, very important. Now, what are the conditions for uptime? So this is the thing I wanted to explain. The screen should be as far as possible, means D should be longer, capital D. The wavelength of light must be larger, okay, and then the two coherent sources must be as close as possible. Okay, so these are the three important conditions for getting better broad interference, clearer and broader interference. Okay.